In this video, we're going to discuss the last section in our piecewise interpolation chapter and talk about cubic spline interpolation. So cubic spline interpolation is the most popular spline interpolation method. The cubic spline functions are sometimes simply referred to as splines. So given k data points with k-1 intervals, we aim to define a third-order polynomial of the form Si of x is equal to ai plus bix plus ci x squared plus di x cubed on the intervals between the data points. So this is shown graphically here. So we've got our k data points, xi up to xk with their associated function values, yi or y1 up to yk. And on each interval between the data points, we define a cubic polynomial of the form shown here. So we have k data points surrounding k-1 intervals. On each interval, there is a cubic polynomial with 4 unknowns, a, b, c, and d. So the number of unknowns is 4 unknowns per interval times k-1 intervals, so 4 times k-1 unknowns. So that means we need 4 times k-1 equations to solve for our unknown coefficients. So we can look at a number of conditions to come up with these equations. And the first is that the function values of adjacent polynomials must be equal at the interior knots. This ensures that the splines pass through the data points and ensures continuity of the splines. So at the interior knots, the function of value from this polynomial has to equal to the function value from this polynomial, and they have to equal to the given data point. So this can be written as shown here, si minus 1 of at xi is equal to s of I at xi, and they're both equal to yi. So this gives us 2k minus 4 equations for the interior knots. The second condition is that the first and last functions must pass through the endpoints. So our S1 has to pass through this point y1 at x1, and our sk minus 1 has to pass through the value yk at xk. So this gives us 2 additional equations for the end knots. So far we have 2 k-1 equations. Next, we can say that the first derivatives at the interior knots must be equal. So this is the slope of this function has to equal to the slope of this function at the point that they meet. So we can write this as shown here. So the first derivative of si at the point xi plus 1 has to equal to the first derivative of si plus 1 at the same point xi plus 1. So this gives us an additional k-2 equations. We can also say that the second derivatives at the interior knots must be equal. So at the point where the two functions meet, the second derivatives also have to be equal. So the second derivative of si at xi plus 1 is equal to the second derivative of si plus 1 at xi plus 1. Again, this gives us an additional k-2 equations for the interior knots. So we can see that we have 4k-1 minus 2 equations, so we need 2 more equations. The last 2 equations come from the end conditions. And there are several options for the end conditions. One of the common methods is called a free runout, or which is also gives us what we call a natural spline. And this is where we set the second derivatives at the ends to be 0. So s double prime of it's the second derivative of s1 at x1 is equal to the second derivative of sk-1 at xk, which are both equal to 0. We can also do what is called a parabolic runout, which is where the polynomials in the first and last intervals are parabolas rather than cubic functions. So this allows us to reduce the number of unknowns. We can also use something called not a knot spline, where the first spline is defined over the interval from x1 to x3 instead of just x1 to x2. And the last spline is defined over the interval from xk-2 to xk. And there are other options as well. So here we will just briefly discuss option A as well as option C. So for the natural splines, the second derivatives at the ends are equal to 0. So this means that at our endpoints, the second derivative of S1 is equal to 0, and the second derivative of S at k minus 1 is equal to 0. So this means we get 4 times k minus 1 equations in total. So the resulting equations using the natural spline technique are shown here. So the first ones come from the continuity of the function at the interior knots, as well as the function must pass through the endpoints. The next ones come from the continuity of the first derivatives at the interior knots. And then the next ones come from the continuity of the second derivative at the interior knots. And then the last two come from our end conditions, which we said the second derivative at the endpoints is equal to 0. The knot-a-knot approach, the first spline is defined over 3 points, so from x1 to x3, and the last spline is defined over the interval, the last 3 points, so k minus 2 to xk. So this reduces the number of intervals to k minus 3, which means that we only require 4 times k minus 3 equations to solve for the unknowns. So in this case, a total of 2 k minus 3 plus 2 equations come from the requirements that the polynomials must pass through the data points at the interior knots and at the endpoints, and the first and last polynomials have to pass through the second and next to last data points, respectively. The additional conditions come from the k minus 4 interior knots between the polynomials. The first and second derivatives must be equal to each other, so providing the additional 2 times k minus 4 equations that we need. So this gives a total of 4 times k minus 3 equations. So the using this knot-a-knot end function or end condition can be graphically represented here. So you can see that the first interval contains, so one spline is defined over this whole interval, and same with at the end, one spline is defined over this whole interval. So this sort of updates kind of the numbering of the equation with in terms of what data points it corresponds to, but otherwise the internal functions are the same as they were defined before. So let's look at an example using cubic spline interpolation with the knot-a-knot approach to find the interpolating function through these 5 data points. So there are 5 data points, so k is equal to 5, and that means we have k minus 3, which is equal to 2 cubic polynomials required for our interpolation. So to find our associated 4 times k minus 3, which is 8 unknown coefficients, we use this the 8 equations shown here, which can be solved for our unknown coefficients. So the first 3 are related to the function values of the first polynomial. The next ones are related to the function values of our second polynomial, and the last 2, this defines the continuity of the first derivative at the interior point, and this defines the continuity of the second derivative at the interior point. So this is how it is shown in matrix form, which we can then solve for our unknown coefficients, which are given here, are a1, b1, c1, d1, and a2, b2, c2, d2. So the resulting interpolating spline is shown here. So we only have 2 functions. The first goes through the first 3 points, and the second goes through the last 3 points, and they have continuity of the first and second derivative at the interior point. And this shows using the same technique for the 11 data points in the Runge function, and you can see that we get a very nice match with the original function, a very smooth curve across the domain here. So cubic spline interpolation is the one that is probably the most commonly used, and it can provide very nice smooth functions.